Okay, so in the last one, we solved the undamped periodically forced harmonic oscillator in the case where omega was different from omega naught. Okay, now I want to interpret and try to understand what that solution is sort of saying. Um, so look here, we in our solution we have this cosine right here. It's got some complicated amplitude, f naught over m times blah, 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 blah. But it's cosine omega t. That's the feeling I want you to have, okay? And then we've got this part here. Now, don't forget, we talked about how you can take this expression and rewrite it, uh, the so-called using the so-called phase, um, uh, I think the phase amplitude um, uh, representation. We could rewrite this part right here as c times cosine omega naught t minus gamma, where gamma was the phase shift. And so what you should observe is that this x is really a superposition of sinusoids with different frequencies. Okay? It's the sum of two sinusoids with different frequencies. Now, one important idea when you have waves with different frequencies and interesting phase values and all of that kind of stuff is the phenomenon of constructive and destructive interference. Okay? But in this particular situation where we have omega and omega naught sort of being unequal to one another, we get a very interesting phenomenon coming out called beating. Let me just try to first illustrate this with a picture, and then show you, in fact, what it sounds like, what beating actually sounds like. So I'm going to open up the textbook. Here is an example problem in which we see that we have omega naught in this case being equal to 4, and we have omega being pi. Now pi is 3.14. Pi and 4 are not the same. So we are indeed in the situation that we've been discussing where omega is different from omega naught. You can go through this example yourself, but the thing that I want you to focus on is the graph of the solution to one of the solutions to the differential equation with a particular set of initial conditions. Namely, you can see the initial conditions in the problem statement. But let me take this picture here. Can I copy it and move it over to my notebook? Allow paste, and there it is. Because the feeling I want you to feel is that there is this sine, this kind of or a sinusoid, which is being enveloped by this other sinusoid. I see sort of two sines in this picture. There's of course this sine, this periodic. I know it doesn't look like a sine, but it's like a sine whose amplitude has been attenuated by something. This is not unlike the envelope curves that we saw before. What is the envelope curve here, though? Well, do you get a feeling like I do that it's again a sinusoid? It's a what we see here is a sinusoid whose amplitude is being attenuated by another sinusoid, by a longer wavelength sinusoid. It looks something like this. These are the envelope curves. I can't draw well, but hopefully you get the picture. Yeah? And what we see is the amplitude gets very, very large and then very, very small. Very, very large and then very, very small. The amplitude of the oscillation gets small and then large and then small. And then large and then small. and then large, and then small. Okay. Can we understand this as a sound wave? Okay, that's my question. So what I've done is I've pulled up a sine, a pure tone, a pure sine sound wave generator from the internet. Here is a tone at 131 hertz. Can you hear that? Wait, is it completely, oh man, is it completely taking over my microphone? Let me turn it down just a bit. You hear that? Now I'm going to play another sine wave. And it'll be initially at some random, here it is, 307. You hear two tones at once. But now what I'm going to try to do is bring down the 307 one lower. Do you hear the beating? Wub, 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 wub. That's the beating phenomenon. And that's what we see in the solutions to these differential equations. When omega and omega naught are close, we really hear this very, very clearly. These were two tones that I played for you on top of one another. One at 131 hertz and one at 135 hertz. Okay, you can do this for yourself. Just look up pure online tone generator. Okay, and you can do this experiment for yourself. Open it up in two different tabs, play around with it. It's fun. Okay, in the next one, we're going to try to understand what happens when omega is equal to omega naught. And here we're going to see yet another interesting phenomenon, very useful phenomenon. It's called resonance. Okay, see you in the next one.